Okay, hello everyone. My name is Hurych. I'm from Valeo company. I'm the last presenter. I'm collaborating heavily with Martin and with David on the Exaformind project, and I will present Valeo use case in Work Package 5 on this project, which deals with autonomous driving, cars, lasers, images, and AI. So I'm part of Valeo AI team. Valeo AI team is mainly based in Paris. So you see some team pictures. Our main goal is to actually do some science and publish data, publish publications, and publish also all the codes. So Valeo has this quite special team which does not keep everything in-house and also shares with the community. So this is the main goal of my team. And also my second team for the last 3 years and for the following 3 months is Exaformind team. You saw a few people here, but this is a nice picture from the meeting in Prague from last few months. And you already heard the details about the project, so maybe I can skip this slide and go into the advanced driving assistance systems and big data processing, which is my main topic of focus. So in Valeo, we are developing advanced assistance systems, which leads from very small assistance systems, which just check the available parking slots, all the way up to level 5 driving. We're not yet there, but soon we will be, hopefully. And in level 5 autonomous driving car, you will not have a steering wheel, you will not have pedals, you will not have everything, right? Right now we're working on L3 and almost L4 systems. So a few applications here, just from level 1 systems, which is very slow maneuvers, for example, for automated parking or up to speeds of 30 kilometers per hour, to level 2 systems where, for example, if you have some adaptive tempomat, basically, or follow me systems where on a highway, on controlled scenarios, for example, highway, you may trigger automated driving, basically, which is able to follow another car, changing lines, braking, automatically speeding up. But still, in level 1 and level 2 systems, the driver is responsible for everything. So any crash that happens, it's your fault. You need to have the hands on the steering wheel and you need to be focused, right? So L2 is assistance system, but nothing like autonomous driving, right? And level 3 systems, this is small breakthrough, because level 3 systems, there the car company takes responsibility for some scenarios. So if there is a level 3 system for up to 60 kilometers an hour or something like that in city or in highway, whatever is the assistance system, the car is responsible. You don't have to have the hands on the wheel, and you need to be able to react within 5 or 10 seconds if the car tells you, because the car can recognize, okay, there's a change in scenario, there's some unexpected situation. Driver, take control, and from a few seconds you need to be able still to take control. So you cannot sleep, you cannot. It's called you cannot be mind off, like the technical term is. You should be still kind of focused, not necessarily completely out of your thoughts. I will talk here not about the AI which is running in a car, detecting pedestrians, detecting cars, etc. This is the usual stuff which everybody knows. I will talk about the AI which we use in Valeo for processing reference system data. What is a reference system? So if you develop a ADAS system which shall do emergency braking for you, before we deploy to a car, to million cars for a customer, we need to validate it. Validation is a very specific role, because we need to first of all validate our sensors. So if we develop lasers and cameras and we put it into the car, we need to buy commercial sensors which are commercially available, put them on the car roof, and drive thousands of hours with this system and with this reference system, and check if our Valeo ADAS does what it's expected to do. So these data, we need to collect them as a statistical campaign, and there's lots of hours of data. You can imagine that if you have one camera, 30 frames per second, times 3,600 per hour, times 10,000. So we have billions of images, really. And every image, every laser scan for every camera needs to be somehow manually annotated to say, here is a car, here is a pedestrian, here you should brake, here you should turn left, right? So it's extremely expensive and not reachable to do it purely manually. So I will talk about AI, which helps us to process such system validation data, which are much larger than the data on top of which the AI is usually trained. And for that, we are able to use supercomputers like the one in Ostrava and many more. So in the car, it runs on a small computer, but to validate the system, we can actually deploy big AI, big models, big computers. So what are the usual tasks that our systems need to be validated on? One may think that planning a maneuver is difficult, right? So if you have some situation which is high speed, somebody's braking, somebody's coming from the left, people need to react quickly and try to perform a maneuver. This is for a car very, very easy when they have a good representation of the world. So if they have understanding in the 3D space, what is around them, what are the speeds, what are the people and cars and animals there, then it's very easy for it to plan a maneuver. But what is very difficult for software, piece of software, for AI, it's perception of the real world. So to recognize what's there, to detect the people, to detect the cars in very low resolution behind, half covered behind some object. You imagine pixels are numbers, right? So is this group of numbers, is it a car? Is it half a car? Is it, do I see the back? Do I see the front? What is it? So imagine that you are just seeing numbers and tell me if it's a human or if it's just some piece of staircase, right? So this is the difficult problem. People can recognize everything perfectly because somehow we are trained for it. It's very natural for us, but for computers, it's still the main difficulty. One of the tasks is object detection. So simply you just have a bounding box, which is a rectangle around every object. You just know this is a rectangle and it's a person. Semantic segmentation, you have label per pixel. Every pixel has a color saying to which class it belongs. Red pixels are people. Violet pixels are sidewalks, etc. But we cannot recognize the instances. I don't know who is Karel and who is Lukáš in the persons, right? I just know that it's a person. So the third task is instance segmentation. I have per pixel labels and I know the instances. I know car A, car B, car C, right? So this is the most complex method, most complex type of perception which we need to do. The same we are doing in lasers. So Valeo is also manufacturing lasers right now, third generation of laser. 3D object detection. This is not bounding boxes, it's 3D bounding boxes. So there are boxes which needs to be placed manually or automatically where there is a car, where there is a pedestrian, etc. Semantic segmentation, instance segmentation. So per laser point, you have a class, per laser point, you have a class and identity. Why do we need the identity? Not like identity who is who, but we need to be able to track the people to see if they're intending to go into the road, if there is a car which is continuing in our direction, etc. That's why we need to be able to recognize in between frames what's happening. And this is something which we need to do on billions and billions of images or laser scans, which is absolutely not possible to do it purely manually. So what is AI, right? In our computer vision task, right? We need to train the perception model. This is an image, black box, and we want this kind of output. This actually is relatively okay. I will just quickly show you some of the results for the task to see just as a motivation how it looks like when it works. So basically, maybe I can pause it. The left video is a combination of object detection. I have bounding box, and I have also instance segmentation, right? So I have knowledge about the object type, and I have knowledge about the object shape and about its identity. This was, we used some AI model to detect and segment these objects. And our annotators, which are supposed to then confirm or repair just the mistakes of the AI. So in any way, the data need to go through the hands of person to check for the mistakes of the AI, but they are not annotating from scratch. For example, this is semantic segmentation, and annotating one such image with pixel precision, it takes more than an hour, 1.5 hours for one image. And then imagine billions of images. Okay, so this is how it looks when the AI does the thing. And on top of that, we are repairing the mistakes in order to validate our systems. Okay, and this is nothing surprising. You have seen this many times. And this is basically this case, given the data, how to train the model. So that's one thing. This is something which we can do already for a long time. And you're not surprised if your cell phone detects your face, because this is called supervised training. You have a lot of images and a lot of manual annotation. Where is the face? Where is the object? From these pairs, you can easily train an AI model and everything works. But in Valeo, in system validation, we are in trouble. We don't have the annotations. We have just the data. 10,000 of driving hours, and we have absolutely no idea what is inside, right? Because we don't have it annotated, we cannot compare. And that's where the research comes. The latest research is actually dealing with these things, how to leverage pure knowledge of the data via some foundation models. Those are big models trained by big companies, which already reveal a lot about the data, and how to bend it and put it into a new task without annotation, or with minimal of annotation. So this is called self-supervised training or domain adaptation training, which means like I have a big AI model which is doing great, but it's super slow, and I can pre-annotate the data for smaller models. So big model is training smaller models. This is called knowledge distillation or domain adaptation. And there is a huge research, literally thousands of scientific papers every year, which are trying to get better and better at this, because it's relatively cheap to get the data. It's super expensive to do the annotation. Maybe connection to large language models. So all of you know ChatGPT and these models. Big part of the model is pre-trained without annotations. So they download the whole internet, just text from internet, from webs. And given the sentence, they just mask one word. They just, okay, I have a sentence and one word is missing, and they are saying, okay, dear AI, predict this word. Given the context, left and right, predict the word. And this is done basically on the whole internet, which is cleaned. And this big pre-training requires these big supercomputers. And then they are fine-tuned on small sets where they have annotated data for task, for mathematics, for whatever, right? But this huge pre-training, this is what allowed to ChatGPT to exist and all the following models. So self-supervised training. Some criteria taken from the data without any annotations. And what do we need? And what we work on the Exaformine project, we need definitely to use the supercomputers. We don't have a supercomputer in Valeo, unfortunately, but thanks to the Exaformine project and to cooperation with the partners, we're able to use mainly Carolina and some other supercomputers like Leonardo with public level data here, Valeo data here, to perform this self-supervised training, to develop new scientific methods, to publish them, and to transfer them into some tooling which Valeo can use. And this is what we actually ideally want. Given an image, I want to understand everything about the image. I want to know, to have all the bounding boxes, all the objects segmented, including buildings, doors, whatever, including the tram. And I want to also be able to ask questions via natural language. I want to write the sentence as a question, and I want the AI to give me an answer with respect to the image. For example, I know that this is a tram. I detected with my detector. Is the tram having doors open or closed? I want to pose a question and I want textual answer. For this, we are leveraging and training and developing so-called vision language models. Those are models which have as an input image and piece of text, which is, for example, a question, and at the output, they have text as an answer. So, for example, one of these models, given this data, there are very ugly images, but they are real images. We don't have beautiful images with nice contrast, etc. We are capturing, this is a parking lot at night time in rainy weather. And such images we need to process in order not to kill people when moving the car, right? Such is the reality. So, for example, the model has a question. This is a question for the model. Give me images of wet road. Then it's giving a bunch of images. And it answers, it orders the images with the probability where there is a wet road. So this is what we get as an answer. Or question, image of parking lot with sun. This is the returned results from the real data from real Valeo project. So not any toy data from any small data set. You see some of them are inclined because it's mounted on the rear mirror in such a way because customer wanted so, right? So we don't even have the horizon always upright. We have fisheye cameras. So really the variety of the data is huge. And we want to understand them when we capture these thousands and thousands of hours where we don't know what's inside. Why we need to understand them? It's clearly because we are responsible for testing of the system on a statistically valid piece of the world. And how do we get these statistics? Well, via AI, right? So we need to train the models. We need to leverage the existing foundation models, these big models by big companies, to discover what's inside of the data in order to say, okay, our system was trained and tested also on tunnels, wet roads, There were also baby strollers nearby, even though we are not annotating them because the customer doesn't require that. We need to be able to answer any question about the data, basically. And this is the attempt that we are trying to do and develop here. I can maybe skip this. So these tools we are developing and deploying in the Exaformine project, thanks to the supercomputer and the cooperation with the partners and all the tooling. Here again, just one more slide, but about the vision language model. Given an image, we can ask the questions, right? So for example, how many cars are in the image? The answer is 10, but it's wrong, because I'm asking vision language model, which just reads the image. It interprets it as a vector of numbers. I'm talking to this vector of number. I'm not talking to the individual objects. In order to ask the question for what is the number of cars, I should run this object detector, which will give me the bounding boxes. That's a specific AI. It's not vision language model. It's just detector. And this would answer the question much better, right? So in this project, we are trying to have a clever combination of object detectors, semantic segmentation models that are discovering the individual objects, and vision language models that allow me to have a question for the whole image, have a question for bounding box only, have a question of subset of image, right? So what is the person holding umbrella? We were lucky to get the good answer, etc. So I can ask anything, and this enables me to later on use natural language for data filtering. I will show you how it works later on. This is some example of open vocabulary object detector. What is open vocabulary? Usually you have this annotated data for 10 types of objects, for example, cars, pedestrians, trucks, whatever, 10 types of objects. But I need to specifically train the detector for these 10 types of objects. Lately, there are models which are combining vision language models and detectors in order to be able to ask for any class. So I just have a data, I have a trained model, and I never trained it to detect the jogger. Not the person, but jogger, somebody that's running. Or this truck crane. I just give it this class at the inference time, at the time when the detector runs, and it gives me the result, the best result possible. Of course, it's a little bit worse than if I would be training it in a supervised way, if I would have manually labeled truck cranes and training for truck cranes, okay? But this allows me to ask for anything with a little bit of a lower precision of the output. One of the scientific results that we have in this project revolves also about point clouds, because we have to validate. Imagine that you have a front camera on your car and it detects a traffic sign which is 25 meters in front of you. But it's a camera. The camera doesn't really know how far things are. It's just pixels, right? It's estimating it via some AI. And we need to be able to validate that the distance is done correctly. So we need to also have the laser on top of the car to actually validate, yes, it's 10 meters away, or such is the distance difference. So we are processing lasers basically, and we don't have any annotations again. And I will show you how in a few slides how we are actually training laser how we are training the AI that recognizes object semantics from the laser. So the meaning of the points. Here what we see is basically when I click a point in the laser, for example here, it gives red color to objects that are semantically similar. So here you see that the cars are being colored in red and the buildings around are blue. This is not a natural property. We need to force the AI to give it such semantics. And this is done via this domain adaptation. How we are doing that? Just bear with me. It's not that complicated. Just I would like to introduce you to foundation models. Foundation models are huge models that are pre-trained on thousands and thousands of GPUs on huge data, which basically only a few companies in the world can imagine to do. This foundation model is called Dino V2. Yeah, V2, and it's trained and released by Meta, former Facebook. So Facebook is really doing a great job for us researchers to release large language models, to release image-based models, which are helping us to deploy some other techniques and to do some more research. So what you see here are images and features. When you pass the image through the network, you have some layers, and in the last layer you will get basically 2,000 numbers, for example. If you take the principal component analysis, which is some projection from 2,000 numbers to 3 numbers, we can visualize these 3 numbers as RGB, red, green, blue. So it's a big compression of what the AI does, but it helps us to visualize the thing. So here are the features visualized as 3 channels after principal component analysis, whatever that is, doesn't really matter. But we see that all the objects, the different body parts have the same color where the semantics is the same. So the wings are always green, being it a bird, plane in different juxtapositions. The head is always red. Okay, for the elephant, the nose is always green, even though it's a statue of an elephant. So such is the strength of the foundation models. It helps us to give meaning to image pixels. And then we can take this meaning and transfer it, for example, to lasers if we have lasers paired with pixels. So this is how actually this model was trained, because we had the pairs of images and lasers. So here you see a laser overlay over image. These are captures from Prague. So the distance of the laser is encoded by color. So yellow is more distant, blue is closer. And here is the just segmented objects on the image, and the projected laser points are just taken for the cars, for example. And if we have these pairs, we can take DynoV2 features and we can force these features to be obtainable from the laser. And we train AI model for that, right? So without any annotations, we are able then to take just the laser and give it meaning. This is one of the papers so this is just the visualization, images, some features with DynoV2. So this we don't train, we just steal it, we just borrow it. And we train AI model for lasers and force them to have the same features without any annotation. So this is happening quite often in many fields, maybe for time reasons, so that I don't put you to sleep, I can speed up. These are right now 9 papers. We have one more in submission, which we published under the ExaForMind project. So thanks to the supercomputers, thanks to the data orchestration, and thanks to this big data processing, we were able to come up with 9 scientific papers published at top conferences, spanning from image to laser processing and also to image generation. So you know image generation very well, NanoBanana, Gemini, whatever. They are generating images. We are also generating images. And why do we need to generate images? I will show you later, but right now I would like to show you a quick. I don't have the guts to show you the demo as David did, but I have at least the video of an app that we are using. But before that, I would like to show you the setup of the car, for example, that we used for capturing Valeo dataset that we are processing. So there are 7 lasers, 6 here, 1 here, 2 stereo cameras. There are GPS antennas, and there is a full trunk of with equipment for recording this data, because the flow of data is very large. So given this large amount of sensors, we have roughly 2 gigabytes per second flowing of data to put it into a hard disk. So several cars are equipped by such equipment, very proprietary, very difficult to get. So the recording of the data is also quite expensive, and it's a science. Here, my colleague Antonin, who is collaborating with us, is explaining his method. I can skip that. I would like to show you the open vocabulary object detector, which is here. So we are detecting trash bins, even though we never trained the AI for trash bins. So we just say in the beginning of the video, we want this type of object, and we get it. Here we are asking just for red cars, red vehicles. So no, we don't want to detect any vehicle. We want to detect this one. Now it was detected, and the second one was detected now, and there will be one more here, also detected. You saw that it was not detected in all the frames because the AI makes mistakes. But since we have videos, for this open vocabulary, we are okay just to detect it in few frames, and then we can track. So we can save for the misdetections. This is blip feature, which is enabling the natural language query, which I will show you here. Just in a second, maybe I will show you first this. So this is some Kibana dashboard where we, given the data and given all the detections, we need to be able to filter through the data. So here we see interactive dashboard where we can make sub-selections of the data. For example, I want images where there are cars, pedestrians, and trucks, and it will filter down the images by few clicks. It will give me subset of the data which is relevant for whatever analysis. One of the main points which we wanted to reach is this natural language query. So here I can write a few sentences about what kind of data I want to filter. So purely natural language sentences, which are using these vision language models, these things projecting images into vectors, and I'm then just talking to the vectors basically. And this enables us to really figure out what is the data, and it can be used by a non-trained, not AI people, not even software engineers. This is a simple tool that enables us to ask for anything and learn if we have it in the data. I will skip the video to the end where I have few images. So these are the queries: image of a bridge. This is what we retrieve. Images of rainy weather with wet road. Purely, you can write even more sentences than just one. Okay. And right now I don't have it yet in the slide, but we have also image to image query. So I can upload an image, and I want the system to give me most semantically similar images. So we calculate these Dino V2 features, which you saw the RGB images, and via cosine similarity, I can retrieve similar data. So I can download an image from internet and see if it's in my database of billions of images just by pure similarity search. And it's running in real time because everything is stored as a vector database, which was also achieved thanks to the partners of VP1 and VP3 from the ExaForMind project. So out of the latest AI, we in this project are trying to, first of all, reach some good functionality also for the lasers, for open vocabulary, and also to get an application that will be super useful for us in the real projects. And 2 minutes left. We are also augmenting data, so we are generating. It's not surprising for you because you have seen many generated images, but we need to have things under control. So for example, here, I want to erase this car, okay? I can train a model that's able to give me this control. I can redraw this car to be different. Why we need that? Because we need to test on many types of data, and we cannot capture them. We will never capture an elephant on a road. So we need to draw the elephant into the road to see what our systems do, right? That's why we need to generate. So for example, here, I make it winter scene. It's the former scene. As you can see, it makes mistakes also. So here is a grass. And while making it winter, it also adds a wall there. So it's not perfect. That's why we still are doing research to have higher and higher control on top of this data. I can make the road wet. I can make the sunshine, etc., etc. And that's it, I believe. I hope you are not too sleepy, but thank you for your attention. And if you have any questions, I will be happy to try to answer.
Thank you. My question is, are there models which can classify a class which wasn't predefined at the beginning of the training? I mean, if it recognizes a pattern, is it able to assign it a number so you can identify it in the post-processing?
Yes, so this is actually the exact goal for the open vocabulary models. You come with your list of classes at inference time. So after the model is trained, it somehow steals the know-how from the vision language model and embeds it into the detector. And at inference time, you have an image, and you just come up with an object type which you want to detect. So that's called, for example, a YOLO world. If you want to reference YOLO world, it's one of the models. And it's also allowed by the vision language models on the whole image level. So basically, it works like that you take, for example, it's called Lava 1.6 or whatever, I can tell you the reference, which encodes an image into vector of numbers. And you then have also your text query encoded as vector numbers. So both are encoded as vectors or numbers, and you just calculate the distance of those two vectors. So the AI is trained to encode it in the same way. And that's how you simply can have the vector database, which is super fast to query. So just calculating distance of two vectors is very fast. So if you have pre-calculated these vectors for all of your images, then you can take your sentence or your question for a specific class or pattern type or whatever, and it translates it into vector and immediately gives you the result from the distance from the other vectors. So it's enabled by two AI models, open vocabulary detectors, and vision language models. Did I answer the question?
Partially. Yes. And are they able to recognize a pattern which occurs multiple times in the data set, even though you didn't ask for it?
Yeah. So this is basically I would say the easiest way to do that is to calculate, for example, the DynoV2 features, and again, vector of numbers, and again, distance. Right now, everything is revolving about this cosine distance on top of features. So this is exactly what it's trained for. It's trained to recognize patterns without any knowledge about the classes. For example, DynoV2. It just takes images. They have no labels. This is human, this is dog. They don't have it. They are just giving you a texture and shape similarity. The texture and shape similarity, the objects of which are then very close in the vector space of the numbers. So any feature extractor, basically any backbone of any semantic segmentation network, I would recommend DynoV2, will do the job.
Actually, I had a very kind of question which is almost embedded in what you explained. I have two questions, and both are regarding the speed. I was wondering how much time it takes you to run these models, let's say for, I don't know, 1 hour of recordings.
Mm-hmm. Yeah, so depending on the model, there are some super fast models, for example, MobileNet. It runs on your cell phone 30 FPS, but there, of course, the precision is much lower. DynoV2 is a huge model, and you have different sizes of backbones, right? Backbone is the feature extractor. You can choose which of the pre-trained is suitable for your application, so you can scale it relatively easily from what is already available. And what was the next question?
It's even simpler for this, let's say, open text query.
Yeah.
How fast it is, but I think.
Yeah. So one of the slowest is actually these vision language models. For example, this Lava 1.6, we are having trouble to extract a lot of data on Carolina. We are consuming the most amount of hours by the vision language model, but it's always given the amount of the parameters. For example, some of the large language models which are freely available have, for example, 2 billions of parameters. Some of them have 34. ChatGPT has something like 450 billion of parameters. So given this amount of parameters, this is not proportional to the inference time. So usually the still very well performing models, which are the smallest, are around 1 or 2 billion of parameters. And then you have the large ones, which are crazy, which even Carolina cannot fit it into one node of Carolina, for example. One node is 8 GPUs. Each GPU has 40 gigs of memory. So 320 gigs of memory. It's not enough to fit some of the large language models, for example, or vision language models. So it's really, you have a plethora of models. You can try to play with them. And of course, the larger, the more precise, the smaller, faster inference, but less precise. Yeah.
I have two questions. How do you identify objects that are small, if they are real objects? For example, small people. Is it toy, or is it real man? And the second question is, do you find some limits of vector representations to find similarity?
Limits for vector to find similarity? Yes. So first question is basically it depends on the resolution. So if usually the rule of thumb is that something that's 10 times 10 pixels, 15 times 15, it's still detectable. Smaller, we have trouble. Recognize if it's a person or a person on a billboard. Usually you just get a detection it's a person. You would have to have something more complicated like the VLM to ask for the scene, and it will tell you there is a billboard, and on the top of the billboard there is a person, because it will give you sentence. But the detector will just give you bounding box on a person on a billboard and bounding box on a real person, right? So certain models can distinguish, certain models cannot. One needs to account for that. And the ask.
Do you use video to?
Yes. So video and motion, there's this so-called optical flow and tracking. So optical flow gives you a motion vector for every pixel in between two images. So I have a lot of motion vectors for every pixel, and you can judge, okay, that's a billboard because all the pixels are moving like that. And this is a person because every pixel is moving somehow differently because person is waving hands, right? So this is one of the features which you can use, or tracking, etc. For the question about the limit for the vector space to recognize objects, that's always a matter of compression of the data. So basically we take, for example, 8 megapixels image, and we create 1000 numbers. So 8 megapixels is 8 million numbers, and we compress it to 1000 numbers as a vector. So it's always about compression, decompression, and the larger the vector, which is called latent vector, the more, of course, the more capability it has to encode complexities, different textures, etc. So the higher the compression, you will just say it's a person. But if you have more numbers there, you can say it's a person with shorts, it's a person with skirt, it's a man, woman, etc., etc. So there is the only limit there is the size of the latent space of the vector and the quality of your AI, because badly trained AI will do bad job whatever the size of the latent. So you need to have good training algorithm and good training criteria to get to your result which you need. But the space itself, you can inflate it. You can just say, okay, I want 2000 numbers for this vector representation. I don't want just 400. You can scale it.
What about the language model of vectors?
Language model of vectors is the same. So this retrieval augmented generation, it's RAG, you give it a document and it creates a vector of numbers, nothing else. And you can have a database of these vectors, and then you have a question about your data, and it calculates vector, compares with all the vectors in your database, and will give you the most relevant documents to your questions. Such a way, this is exactly the same. So being it text or image or laser, you can always compress it to vector of numbers and then talk to it via cosine distance. So there is not any limitation on top of what kind of data you put in. It could be laser, it could be radar, ultrasonics, whatever.